Welcome students, myself Rahul Kotkar. In this video we are going to discuss about the chapter Mechanical Properties of Fluids. It's our lecture number 9. To the previous lecture we studied about the factors affecting the angle of contact, factors affecting the surface tension. In this video we have to discuss about the Laplace law. This Laplace law is related to the spherical membrane. You may also call it explanation of formation of drops and bubbles. Means how the drops and bubbles are formed, that will explain here. So that is also called Laplace law of spherical membrane. Let here we consider a spherical drop. This spherical drop having Pi with the pressure inside the liquid drop. Po or P0 is called pressure outside the liquid drop. This drop is spherical in nature, and so its inside pressure is greater as compared to the outside pressure. Means the pressure inside the liquid drop should be greater as compared to the outside pressure, and that's why it have a spherical nature. So therefore, as you have Pi is greater than P0, then what we can do for getting the excess value of pressure inside the liquid drop, we make a subtraction of both. That's why Pi minus P0 is excess pressure inside the liquid drop. Let here you can observe the diagram. What you observe here, as r be the radius of the drop, which increases from r to delta r, means it will be increases from r to r plus delta r, where this delta r is the small value of increase in the radius, and so pressure inside the drop remains almost constant. It's a simple thing. As r be the radius of the drop, and when it increases from r to r plus delta r, here we consider that delta r is having a very small value, means a liquid drop will expand by a very small volume. So therefore the pressure inside it will remains the almost constant. Let here we consider that Ai be the initial surface area of the drop. You observe the diagram. Ai is what? Initial surface area of the liquid drop, means before expansion, initial area of the drop is 4 pi r square. As we have here, which is 4 pi r square, then AF be the final surface area of the drop. As you observe the diagram, what is that? After the expansion of the liquid drop, its surface area is called final surface area of the drop, which is 4 pi into r plus delta r bracket square. So therefore, by expanding the r plus delta r square using the formula simple as that of the expansion of a plus b bracket square, which is equals to a square plus twice ab plus b square. According to this formula, we will expand this term r plus delta r. So what we have, 4 pi multiplied by r square plus 2 times r into delta r plus delta r square. Then as you multiplied by 4 pi to each term, you will get this one, 4 pi r square plus 8 pi r into delta r plus 4 pi delta r square. But as we observe, delta r is a very smaller, and so its square should be neglected. It's simple one. If suppose we consider the 0.1 value, So if point 1 is smaller, then its square becomes equals to 0.01. Means what? Square of the point 1, okay, is again smaller as compared to point 1. So means what? This is again smaller, so this can be neglected. Okay, so that's why as delta r is smaller, then its square will be get neglected. So therefore your term becomes f is equals to 4 pi r square plus 8 pi r delta r. Okay, so therefore increase in the surface area dA, increase in the surface area dA, okay, means change in area can also be say here, that is AF minus AI, final area minus initial area, and which should be by using the both equations of final and initial, that becomes equals to 8 pi r delta r. Okay, so in case of this, work done in increasing the surface area by dA stored as a excess surface energy, means when the sphere expand from initial area to final area, so how much work done will be done there? That work done is stored in the form of surface energy. So therefore work done is defined as, in terms of surface tension, work done is equals to surface tension multiplied by surface area, and therefore it's equals to, by substituting the value T multiplied by, what is the value of dA as the from previous equation, what we say, 8 pi r delta r, and this is our equation number 1. Then again, the work done can be also defined in terms of force, that is a work done is equals to force into displacement. So this is our equation number 2. Here what is the F? F means the force, but here the excess force which will be used to expand the sphere or for expansion of sphere, and this excess force is given by excess pressure multiplied by surface area. By using a simple definition of pressure, P is equals to F divided by A, and so therefore F is equal to P multiplied by A, and that's why it is what? Excess force, and so excess force can be given by excess pressure multiplied by surface area. So by substituting these values here, F is equal to, means excess force is equals to excess pressure, and that excess pressure is your Pi minus P0 into surface area, that is your 4 pi r square. So therefore dW is equals to work done is equals to Pi minus P0 into 4 pi r square into delta r. So in this manner work done is equals to Pi minus P0 4 pi r square into delta r, and this is your equation number 3. Okay, so after that compare the equation 1 and 3. As you observe there, both are the equations of work done, and that's why what we are doing, there is a comparison between them. So we'll get, okay, T into 8 pi r delta r equals to equation number 3. Okay, so as you observe here, the things are common. 4 is common in both equations, so it get cancelled. Delta r is also remains constant, as well as r is also common, and so we cancel it, and we have a remaining part T multiplied by 2 times r. Okay, and here on the RHS side Pi minus P0 only, and so by using that what we will write, so Pi minus P0 is equals to 2T divided by R. So in that case, as you have a relation in this case, okay, so actually here we have a relation in this case, that is T multiplied by 2, and this R will remains as it is, which will make divide here, and so this relation will have T multiplied by 2 divided by R. Okay, and so we can write it in the next step, that is 2T divided by R. Okay, so after that, this equation gives excess pressure inside a liquid drop. Okay, means using that we will calculate the value of surface tension, okay, as well as the radius as well as excess pressure. Okay, means this equation can be useful for getting all these things. If you know out of the three you know the two quantities, so you can determine the remaining one. So in this manner, this is the explanation related to the formation of drop, okay, which is also called as a Laplace law of spherical membrane. In the next point, that here we have to discuss the explanation of formation of bubbles. Okay, so you can observe this equation carefully. What you have, it's a simple one, okay, and just make one single correction here. That is what it will have, the value T into 2 times R. Okay, instead of that it is a value T2 divided by R. Okay, so next point, that is in case of the bubble. Okay, the explanation of formation of bubble. In case of soap bubble, there are two free surfaces in a contact with air, the inner surface and outer surface. Okay, as you observe the soap bubble, or you may call it soap film, in that case what we have, will have there is the formation of bubble in such a way that it will have a two free surfaces in a contact with air, outer as well as inner. And so we have an equation of the drop in which we will write dA is equal to AF minus AI, which is equals to 8 pi R delta R for a single surface. But in case of this will be changes to, okay, in case of soap bubble it will be changes to dA is equals to final area minus initial area, and here 2 times 8 pi R delta R. Why we introduce this 2 here? Okay, because it will have a two surfaces which are in a contact with the air, that is the inner surface as well as outer surface. So work done in increasing the surface area by dA is stored as a excess surface energy. Okay, so work done stored in increasing the surface area means while increasing the surface area by dA, how much the work is stored, okay, that is stored is nothing but what, your surface energy. Okay, means in short, you know that there is a work done is nothing but what, the kind of energy, the amount of work done for increasing the surface area is nothing but your excess surface energy. So therefore dW is equals to T multiplied by dA. Okay, just you have to put the values, instead of 8 pi R delta R you will write there 2 multiplied by 8 pi R delta R, and this equation becomes simple. So again work done in terms of force as well as displacement is given by dW is equals to F into delta R, where F is the excess force and this excess force have a explanation, that is a formula, excess pressure multiplied by surface area. Therefore excess pressure is what, Pi minus P0, and surface area is what, 4 pi R square. So then dW is equal to Pi minus P0, which is equals to 4 pi R square into delta R. Then comparing the equation 1 and 3, again same thing, what we get, T multiplied by 2 in bracket 8 pi R delta R is equals to equation number 3. Okay, again same thing here, T into 4 divided by R. Again actually there should be the quantity T multiplied by 4 divided by R, which is equals to Pi minus P0. Okay, and so the finally we get Pi minus P0 means excess pressure is equals to 40 divided by R, and this will be applicable in case of soap bubble. Okay, means this equation gives us the excess pressure acting on a soap bubble. Okay, so friends, in this manner we have a relation related to this explanation about formation of soap bubble and liquid drop. Okay, so the next topic, capillary action. In case of capillary action, first we have to study what is the capillary tube. A tube having a very fine bore. Okay, you may call very fine bore means what? Very small diameter, approximately equals to 1 millimeter, and open at both ends is called a capillary tube. Okay, what is a capillary tube? It's the having very small diameter and open at both ends is called capillary tube, which will have a thickness approximately equals to the thickness of hair. Okay, so one end of a capillary tube is dipped in a liquid which is partly or completely wets the surface of capillary, like water in a glass. Okay, the level of the liquid in the capillary rises. Okay, listen carefully what is the given here. If one end of the capillary tube is dipped in a liquid which is partially or completely wets the surface of the capillary. Okay, the liquid should be selected or chosen in such a way that which partly or completely wets the surface of capillary. So in such a case, what is the example? Like pure water in a glass, or you may call the kerosene in a glass. Okay, are the examples. In that case, means in such a case what happens, liquid will rises in the capillary. As you observe the figure, what do you have here? The level of the liquid. Okay, level of the liquid in the vessel should be here, but liquid rises in this case. Okay, so it is an example related to what? The liquid which is partly or completely wets the surface of capillary. Okay, then next, on the other hand, the capillary tube is dipped in a liquid which does not wet its surface, like mercury in glass. The level of the liquid in the capillary drops. Okay, means what is here? You observe in case of this mercury. Okay, this is the actual surface of mercury in a vessel, but you dip the mercury inside, capillary tube inside it. So what happens? In this case, the capillary tube, okay, will not make a contact with the liquid, or liquid will not make the contact with the capillary. Okay, means which will not wet the surface of capillary, and that's why the example is here mercury in a glass. So what happens? The level of the mercury falls down. Okay, so for this such a condition, the example is mercury in a glass, which will not wet completely to the solid surface, and that's why it will falls down. So in this manner, this is about your capillary action. And so what is the capillarity? Capillarity is the phenomenon of rise or fall of liquid inside a capillary tube when it is dipped in the liquid. Okay, means you observe there, in case of water, what happens? There is the rise of the liquid in capillary tube, while in case of mercury, what you observe? There is the fall of the liquid, means mercury, inside the capillary. Okay, so this phenomenon of rise or fall of the liquid inside the capillary tube, okay, when it is dipped in the liquid, is called capillarity. Okay, so we have to study here examples of capillary action. So first example, oil rises up the wick of lamp. Okay, so everyone know in the festivals like Diwali, we will lightning the lamp. Okay, so we will use the oil and the wick, okay, which is made up of a cotton. Or in the previous days or some days ago, we are using the kerosene lamps also. Okay, so how they will be get ignite because of the this capillary action, which will, what happens, the kerosene or the oil in it get move upward. Okay, means that oil or the liquid will rises in such a way that, okay, so it will be get lighten. Then cloth rack sucks water. Cloth rack sucks water means what? Okay, as you are using every it's a common phenomenon. Okay, if the water is poor on the surface, we are taking a cotton cloth for absorb the water. Why? Because it will have a good capillarity action. The cotton thread sucks the water, okay, and we can make easily clean. Then water rises up the crevices in the rocks. Okay, everyone know that the water present inside the earth surface, so that will be taken out, okay, using this phenomenon, because crevices means there should be the gaps produced in a rock, okay, because of what? This capillarity action. Means the liquid will be get moves from inside the earth towards the outside. Sap and water rise up to the top most leaves in the tree. Okay, in many more leaves the sap, okay, and water will provided from the earth surface. Okay, the roots are collect it and will provide to the topmost part, that is a leaf of the trees. Blotting paper absorbs ink. We have a good phenomenon in the restaurants. Okay, so what happens there? We are using the blotting paper, either we call it as a tissue paper also, for soak the water or for cleaning the hands. Okay, means what? That will easily suck the water or absorbs the water which present on our hands easily. Okay, and so that is blotting paper absorbs ink. Okay, so friends, in this manner we have observed the examples of capillary action, definition of capillarity action. Okay, so if you have any doubt related to this lecture, can ask in the comment section. Thanks for observing the lecture. Thank you.